Hey folks, how's it going? It's Rob. I'm coming to you here with a little video on Math 130 problem set number 2. All right, so in this video, what I'm going to do is I'm going to walk through some of the problems here, and I'm going to break down how they went, kind of give you some tips on things. And so I encourage you, depending on how the outcome of the problem set was for you, or if you have any maybe lingering questions, to please go ahead and maybe find time with me during office hours or schedule a time, or maybe if I've got a pop-up time during the week to seek me out then. But again, I'm not going to necessarily go deep dive into every question, but I will try to give you the idea behind them and maybe have a couple of pointers as they arise, okay? So the first problem here was about zeroing out, and in this case, what you needed to do is you need to find the domain and the zeros, okay? So if I go through here and find the domain and the zeros, things to note, remember with the domain that you generally start by assuming it's everything, okay? So what you're looking for is clear, incontrovertible evidence, so to speak, that it is not everything. So things to look out for, again, denominators of 0 and square roots of negatives. So for example, in A, B, C, and H, there are no denominators at all. So that would not be a concern. And similarly, there are no square roots. So that would not be a concern. So absent those, A, B, C, and H should automatically be considered all real numbers. You shouldn't even think twice about that. There's no denominators, there's no roots, so there's no possible issues that we could come up with that would cause a problem in terms of plugging in numbers. Okay, so there's got to be no doubt in your mind there. Now, for part D, there is a denominator, okay, except for the denominator, it is 3, and it will never be able to be 0 because no matter what you plug in for T, you will always get a value that will work because the bottom is never going to be 0, okay? Now, in terms of other things, there was a square root. My apologies on G. It looks like there was like a mix-up of variables, so I'll go ahead and fix that. Hopefully that wasn't too much of a mix-up for you, but again, it's something I'll take a look at. My apologies there. In terms of zeros, so things to think about for zeros. Again, so here's the thing, folks. B and C, that just comes down to factoring, folks. So look, the reality is I need us to, those are some, I don't know, pretty straightforward factoring problems, relatively speaking. So, we are going to be doing quadratics in the upcoming week. If you're still someone who's struggling with factoring quadratics, we really got to talk and we really got to get on that because factoring, those ideas are going to continue to come up all semester in some way, shape, or form. So we really got to address those issues with quadratics now because as I've been saying, right, kind of my ongoing thing, we have to assume that this is known. I don't really have time to go into a detailed, like, factoring 101. I usually would probably do that in Math 115, okay? Nothing personal. I just don't have time to do that again, okay? Because then factoring comes up in D, E, and G, okay, when we need to find the zeros. Okay, you can see we need to factor the top. In this case, we actually need to factor both because the denominator. Now, for the domain, when you have denominators of 0, you can just go ahead and specify, say y is not equal to, or whatever the letter is not equal to. That's fine with me. Okay, F, you can see G, I switch those to F. G, again, for the domain, we want the thing. You take the thing inside of the root and you set it greater than or equal to 0. You solve the inequality. Okay. Now, one thing to note is that with radical equations, like you see here in the zeros, it is required that you do check your work by plugging back in because radicals have what we call extraneous solutions. This is going to happen when we go to exponential and logarithmic functions in chapter 3. Basically, this is the idea. When the problem that leads to the extraneous solutions, in a sense, happens right here, okay? Right where I just boxed. When we go to mitigate that radical by squaring, what happens is the number on the left, or whatever side that just the constant is on, it's going to end up becoming positive or 0. Now, that might seem okay, but the problem is this. We know that the value of a square root, when we evaluate it, must be a positive number. So when we solve, what we get is a positive number. But if we wanted the root to be equal to a negative number, that's a problem, and you aren't going to see that because the squaring kind of hides that little issue. So when we get the 18, what you're going to notice when you plug in 18 is that it doesn't work. You do get 9, but the problem is, right, so you get 9 in the root, you take the square, you get 3, but when you add the 3, you get 6. You don't get 0. So technically, there are not any zeros, okay, for part F. All right, so that's basically how those ones go. H is requires a method called factoring by grouping. That is, again, kind of a skill that would be talked about in like a college algebra class. So factoring by grouping, it's just based on the greatest common factors. So you'll find that maybe the first, sometimes you do need to rearrange in some special cases, but you'll find that you've got some greatest common factors such that when you remove them, there's a common thing left over, which allows you to then take that common factor of that common v minus 1, take it out, and then take those two pieces and bring them together. Okay, so then just remember, when you are factoring, you do need to factor completely. You could just directly solve the equation v squared minus 4 equals 0, right? Just like how v minus 1 equals 0 would suggest that v equals 1. And then if you solve this, you would get plus or minus 2. So that's another way to see it. But it is important that you identify all solutions. And that's the thing, a lot of people miss the negative when you work with the square root. All right, functional finance here. One thing, this is like a financial math related question. So with the fixed costs and the variable costs, one thing to notice is as they sound, as the name maybe suggests, fixed costs mean that you pay this cost no matter what. So an example I talked about once, student is think about the rent or your mortgage. If you pay rent or if you have a mortgage, right? If you go and you spend a month on a vacation in another country or whatever, you have fun, you're having fun time, you're still going to have to pay the rent or the mortgage, right? That's a fixed cost. No matter how many, you could spend 15 days out of the month there, you could spend 30 days out of the month there, you could spend none of the days, you always have to pay the rent. That cost to you in your life is fixed. Now, on the other hand, think about groceries. Maybe you move in with your parents or something and they take care of your groceries and you pay your rent. So you pay the rent all the time, but depending on how much you eat, that's gonna determine how much your parents are paying for your groceries, right? So if you eat a lot, they're gonna pay more. If you eat not anything, they won't pay anything, right? So it depends. So similarly, businesses have fixed and variable costs. If I'm like a business, right, I've got to pay for my store, right? I got to pay, the rent. I got to pay certain costs related to maybe marketing. Maybe I have like a fixed marketing budget that I pay every month, no matter how much I sell. I devote a fixed amount to that. Okay, so I have a bunch of fixed costs, and then I've got variable costs. People would consider labor in a sense of a variable cost because the more of something I produce, the more hours of labor I'm going to need people to help me produce it. Things like that. So we have variable costs. Packaging. The more things I produce, the more packaging I'm going to need to buy to package all the things I'm producing, right? So that varies. It varies based on the number of items. So that's the idea. So the fixed costs plus the variable costs equal the total costs. Now in B, the way the average cost works, as my note states, is that it just takes the fixed costs and it divides them evenly. So if you ever trade stocks, right, one way to think about it is this. So let's say that I trade stocks and every stock costs me $10 per stock. So how much I'm going to pay for the stocks vary. If I buy one, it costs me 10. If I buy two, it costs me 20. If I buy 10, it costs me 100. It varies based on how much I want. But then there's a commission of $6. And if you've ever traded stocks, you know the commission, it doesn't matter. You buy one of them, you pay $6. You buy 1,000 shares, you pay $6. You buy 1,000,000 shares, you pay $6. It's fixed. So if you ever buy stocks, one thing you might notice is how much it was paid, what may they call it, the cost basis, the amount that it cost you, that, you know, because if they want to say, well, how much profit have you made, right? When you think about the stocks. So the profit that you made, it's not just the difference between the current value, right? Because you also paid the commission. So what they do is they typically say $10.60. So what they do is they take the commission. If let's say you buy 100 shares. They say or 10 shares. They say each share costs $10.60. Because if you bought 10 shares, it would be $100 plus the $6 commission is $106. So per share, it's $10.60 because they take that $6 and divide it evenly among the shares. So it's a similar idea. You're taking those fixed costs and you're thinking about, well, the items I produced, there was fixed costs that were going on there too. So how much fixed cost, if I divide it evenly, was associated with that? And that's something you want to think about, right? Because if you're trying to make profit, you need to think about how much of those fixed costs is each item I'm selling to going towards, right? Because for each item you sell, right, you're going to pay some of your fixed costs back, but you also need to think about making enough to pay back those variable costs. All right, finally, part C, that was a little bit confusing, so I did reword this, and in the future, and by that I mean after fall 2020, I am going to be looking for the break-even point. So the break-even point is the point at which the amount you earn in revenue is equal to the amount of your costs. So by setting both sides equal, right, each game is sold for $54.95, right? Because again, for each item, you need to make up the $4.95, but then look, if you don't make up your fixed costs, right, those are still there. So you got to pay some of those as well. So you need to make at least 2,700 items so that makes up for all of your fixed costs as well, right? So you can see the $54.95, $4.95 of that comes from the item is being taken care of. And then that leaves an additional $50 to go to your fixed costs. So you need 2,700 items sold to make that break-even point, and then starting on the 27 and first item, you would be making $54.95 in profit, and then so on and so on and so on. Okay, making a difference. The key here, these were the difference quotients, so you just really wanted to simplify them as much as possible. In the first one, you can see there's a lot of canceling. This is one similar to what we discussed in class. Okay. For B, this involves cubing something. So remember, to cube is to multiply it over and over. I suggest using the box to make it a lot more organized. All right. In the end, you can see that all of the H's cancel out here. So if that's something that you can do, you should try to do that. But remember, you can only cancel with a denominator if this entire denominator is in every single term in the numerator. Otherwise, you've got to leave it. All right, part C, this was a little bit challenging because you had to set up a quotient. So just make sure when you do that here, you start, let's work on the top, and you just got to remember to multiply the top and the bottom by the same thing. So those fraction denominators are equal, so you can then multiply, or rather add or subtract across the top or the bottom, okay? When you're done, it's helpful to push that denominator down. So we took this denominator, push it down to the bottom. Okay, but then remember, you aren't done here. You do need to factor. When I say simplify, I mean you got to factor it as much as possible. If you see like terms, right? Or rather, not like terms, but greatest common factors, you got to remove those. And so when you do, you see this is a difference of squares. So we're looking for real big time simplification. D and E, you actually don't end up getting a lot of simplification. I think in the future, I'm going to change the 5/3, but at least here, I don't really see much simplification that you can really do. I'll take a look at the answers and I'll kind of see where things go from there. All right, 4 was another tricky one, folks. So again, 4, you do want to find domain, range, roots, and even, odd, both, and neither. I did ask a domain question already, so you know, think about some of those same principles still apply. I'm probably not going to go into that in so much detail. Range, I would have suggested going on Desmos. Again, I'm probably going to simplify this in the future. I may eliminate the range. And then zeros, you just want to make it equal to 0 and solve. You know, again, kind of similar to question 1, setting it equal to 0, thinking about those strategies like factoring, remembering you really do need to take a critical eye. And when you see something with x squared or an x that's not a power of 1, be open to thinking about it and asking yourself, can it be factored? And why I'm thinking about this is in calculus, you're going to run into situations where you're going to be expected to look at things and be able to instantly see, okay, let's try to factor this and see what happens. So just putting that out there. It was something that kind of startled me at first in calculus, so that's why I thought I'd pass that kind of like advice along, okay? So again, as you see, 2 would have required Desmos. That was pretty challenging. And I'm gonna, as I noted, I'm gonna be grading part B pretty leniently with respect to the range there, okay? All right, not too much to say. Again, the third one's a radical. The x squared ends up making it a semicircle, so that's an interesting one as well. All right, particips, just quick. So A, a function with a square root cannot have a domain that is a set of real numbers. That is actually not true. It's only not gonna, it will only not have all real numbers if there are numbers that make the number under the square root a negative number. So for example, x squared plus 1 is never negative. There's no x that will ever make that negative, even straight up x squared. But here's the thing, the square root of x squared can kind of be simplified. So I did one that couldn't be simplified any further. So my example salvage would be a function with a square root cannot have a domain that is the set of real numbers unless the expression inside the root is positive or 0 for all possible values of x, because then everything will be good. Okay, so if you B, it's like technically false, but like the answer is like, so if you said, all right, well, any possible one, okay, technically it's false. So the idea is if you allowed kind of trivial, like f of x equals 0, because here's the idea. If a function is odd, then f of x equals f of negative x. If I flip the input, it doesn't affect the output, the sign of the input. And then for odd, if I flip the sign of the input, it flips the sign of the output. That's an odd function. So to be even or odd would mean that both f of x equals f of negative x, but also f of negative x equals negative f of x. But because of how equality works, if 2 different things are equal to the same thing, then those things are also equal to each other, right? If x equals 2 and z equals 2, then x equals z, because those are each equal to the same thing. So they're also equal to each other. And I guess 2 kind of looks like z. So if I make them both 3, then x is equal to z. Still the same idea applies. Okay, so technically only f of x equals 0 satisfies this, because 0 is the only thing that's equal to negative itself, right? Because otherwise no function is equal to its opposite. Think about it. What number is equal to its opposite? None of them are, except 0. If you're thinking constant functions, right, those don't work either. So technically you could say a non-constant function can be odd or even, but not both odd and even. You could also say a function that is not f of x equals 0. I did non-constant function because I thought that would kind of eliminate anything in the realm of that kind of issue. All right, not necessarily true for part C either. C says a reflection and a translation is the same as a translation and a reflection. This has to do with, if you think about it, let's say that I wanted to do x squared. I want to do a transformation and a reflection. So if I first do an upward shift, it's going to look like this. Then if I do a flip over the x-axis, it's going to look like this. But if I did the flip first, it would look like this. And then so actually no. So if I do, let's go back. Start again. So we'll start with x squared. Okay, so again, if I first translate it up by 2, it becomes this. If I reflect it over the x-axis, it becomes this. If I start with the reflection, it becomes this. And then if I move it up, it becomes, so you can see these two are not the same. So the fact that I translated it matters. But take a look at how left and the right works different. So if I first moved left by 2, so let's start with x squared. If I first moved left by 2, right? If I moved first left by 2, that would be like doing x plus 2 squared. Now if I flip, I put a negative. Now the flip first would go like this, but then to do the plus 2, see what I would do? I'd have to do this. So you can see that it depends on the type of translation. So I'm not going to suggest a fix, but I thought I'd point that little thing out. All right, D is definitely false. All polynomials will have at least one real zero. That's definitely false. You can think of many counterexamples to this. One good counterexample to this, let me get back to this. Where we were. One good counterexample is x squared plus 1. That's never going to be 0, okay? So there's no real fix for this involving real numbers. That would be very interesting. But again, I'm eager to see what you wrote. All right, number 6, odd and even. I think I just talked about this a little bit earlier. The idea is all even functions, when you flip the x, it keeps the y the same. And then for odd, when you flip the x, you flip the y. So that's all I would say there. And then last one, writing an equation from the description. Just remember the different ways that you would do this. I kind of thought of ways of checking your answer. Just remember that if you put the minus, so if you put the minus or the plus outside, it moves it up and down. If you put it inside, it moves it left and right. Remember, the left and the right is kind of counterintuitive. And then if you put a negative, and if you multiply everything by -1, it flips it over the x. If you flip the sign of the x, if you put a negative in front of the x, that is, right, it flips it about the y-axis. And then there's other things that will do stretches and shrinks, right, and all kinds of stuff like that. So that basically takes us to the end of this, folks. Hopefully that helped answer some questions you have. I'm looking forward to looking at your work and looking forward to a great problem set 3. Have a wonderful day. Thanks for watching, and I'll see you next week.